And hi, welcome to this video. Today we want to talk about dealing with the temperature solver, which is I guess comparatively easier than the volumetric solver because this is a quadratic equation rather than a cubic equation. Okay, without further ado, let's start. How are we supposed to solve for temperature? Okay, so the last time we talked about this, you basically need an equation based on the molar volume and pressure, and you find a quadratic equation in using the square root of temperature. Okay, so why is that so? If you take a look at this equation here, we have the temperature in Kelvin here. However, we also have alpha T. Alpha T here is definitely, most definitely based on the reduced temperature, and there is a square root term in here. So we don't have a choice, but we really have to deal with this square root term. So how do we deal with this square root term? All right. So you will immediately notice that for the temperature, to solve for the temperature in square root of temperature, we will need to define a new unit. Okay, we need to define a new unit. Unfortunately, that isn't quite a trivial thing for the units of measure. Okay, that's not quite a trivial thing for units of measure. You can use something called a type alias to define a new unit. I'll probably leave the description linked in the description. Okay, this is issue number 244. It's how to use type aliases for new combined quantities. So you just follow this, and basically you see here, if you want to make a new type or new unit, you can define this quantity and you fill this in accordingly. So these are the 7 SI base units. Z0 means it is to the power of 0. N1 means to the power of -1, P1 means to the power of +1, N3 means to the power of -3. So do go and take a look at this, but that's one way you can try and do things. My concern about for this method is that for temperature, this is actually unfortunately in a square root. So there's no good way. This is to the power of 0.5 basically, 0.5. However, these are over here are integer values, so I am not entirely sure that you can have a unit to the power of some decimal or floating point value. Maybe you can, but I'm not too familiar with this. So I'm not going to overcomplicate things. Okay, so what is one other way you can make use of the units of measure besides type alias? Now the second way, the second thing we can do here is to divide, or rather convert this temperature, this RT, this temperature here into a reduced temperature. Okay, reduced temperature is simply the temperature in Kelvin divided by the critical temperature. So if you have that, you will be able to make all your units sort of dimensionless. So that's what I aim to do here. Okay, so for temperature solution, I want to make the equation in terms of reduced temperature. Okay, and this is of course TR. Okay, which is dimensionless. Okay, dimensionless quantities are a lot easier to deal with when you talk about units of measure. Okay, so how do we do it? So let me copy the Ping-Robinson equation over, and let me divide throughout by the critical temperature. So I'll divide by TC on one side, and I'll divide by TC on the other side as well. So okay, let's see whether this compiles. That should compile. Oops, wrong one. Rust Simulation Learning Journal. Let's go to docs. types compile real guesses dot type. Okay. All right, it's over here. Okay, the LSP usually takes care of the compilation for you, so don't need to worry unless there's some sort of error. So this is what we can do. We divide throughout by TC, and oops, T here. Let's replace this with TR. TR. Okay, so on the right hand side now everything's dimensionless. And let me move R to the bottom so that yeah, I divide both sides by R. Okay. So yeah, I'll just move the R to the bottom here. So this whole equation here should be dimensionless right now. So what do we have that is known? What do we have that's unknown? So we have P, which is known. In this case, we need a P and a V, a PV value. P and V are known. So P is known, V and B, all these are known. Okay, all these are known. V minus B over RTC, this is known as well. So that can be sort of, we don't really need to worry about it. Okay, so yeah. Well, let me tidy up this equation a little bit more. So that is okay, let's see. Temperature solution. I'm going to tidy this up a little bit more so that it's easier for us to see. So I'm going to cut this out. I'm going to paste this here first. And then I'm going to paste this here. Okay. That's how I want to do it. So we have three groups of things to calculate. This PV minus B over RTC, that's one. V minus B over RTC over this whole volume term here. Then I need this A term as well. This A term, I want to expand it out. Okay, I want to expand it out so that it's very clear what I need to do. Okay. All right. So let's do that. Where are we? Yes. So I'm going to bring this out. I need to substitute what the A is. A is this 0.524 times alpha t. Okay, and that's okay, so that's the alpha t term. Now this is messy, but at least this 0.545724 r square t square over PC, all of this is known. And then I want to sort of do some cleanup first. So this r square tc square will cancel with this here. Actually, maybe I don't need to do that. Okay, maybe I'll leave it as that. I'll let the code do all the calculation. Okay, but it's a little bit messy, as you can see here. But I'm gonna bring in this alpha t so that I can see the whole equation in terms of TR. Okay, let's see. Okay, so alpha t. So we have this messy bunch of equations here. Okay, so for simplicity's sake, let's call this let's call the terms I guess A1, A2, A3, something like that. Okay, what I mean here is let's simplify the terms, so at least it's more bearable to look at. Okay, so I cannot use A1, A2, and A3. So I'm going to use maybe something like psi. Okay, to psi and phi. Psi or psi and zeta. Okay, so I'm going to let psi equals to this thing over here. This first term on the left will be called psi, or I'll just call this psi 1 and psi 2. Psi 1 and psi 2. Okay, so the psi 2 is this whole thing right here, just short of the kappa. Yeah, that's the coefficient of the kappa thingy. So let's me do this. Okay, that's not doing well. I needed to copy all the way to the bottom and I did not. Okay, so let me see this. This should go to the bottom as well. No, that's wrong. That's wrong. I have to restart. Okay. Going to do to the last bracket. Okay. Okay, let me do this first. Okay, so I will delete it to the square. And there you go. Okay, so that's what psi 2 is supposed to be. So at least I can do something like this now. Okay, this is because I want to make the equation a little bit more readable. Otherwise, it'll be quite a nightmare to manage all of this. So I'll just call this psi 2. So I have psi 1 here and psi 2. So so psi 1 is this term on the left, psi 2 is this whole mess of terms on the right. All this should be known at the calculation time. Okay, so now what I need to do is just to expand this out. Okay, so let me just do that. Okay, so it is 1. So I have a 1 minus tr square here. Oh, okay. Let me just do the expansion. Looks like there's like no choice but to do this. Okay. Kappa 1 minus tr. Okay. No, brute force it. No, what choice do I have? So okay. 1 plus 1 square plus kappa square, whatever the tr square is. I'll have to do this like so. And then I need to have a 2 kappa term. 2 kappa 1 minus square root tr. Okay. So, okay, let's check a square, which is 1, 2ab, so 2 times 1 times kappa 1 minus tr, and then b square. So k kappa square and this whole thing square. Then we need to expand the quadratic thing again. But before that, I will need to do some tidying up. Let me tidy up a little bit first. So 2 kappa goes here. Okay, so the 2 kappa goes in here. And let me take out the brackets. All right. So there's a 2 kappa term here. There's a 1 here, and I will need to expand this out, this term out. Okay, so bear with me, do be patient. So for this term here, it is simply 1 minus 2 square root tr plus tr. So that should be the correct expansion. Okay, so that should be the correct expansion. So I have a kappa square term, 2 kappa square tr, and a kappa square tr. Okay, so I'll need to collect all the terms, and then we solve the quadratic formula. Okay, so let's see. I will put in the kappa square first. Okay, kappa square, and kappa square. So let me remove the brackets. Okay, so we have this mess of terms here that we have to deal with, unfortunately, but yeah, let's just do it. Okay, 1 plus kappa square. There's a tr here. So yeah, I can group them based on coefficients. So 1 plus kappa square. Okay, 1 plus kappa square, and then plus 2 kappa. So I'm going to put the 2 kappa in front. Okay, so I'm going to group this together. Next thing I'm going to try to group is the tr term. Factorize that as well. On the square root tr term. So minus 2 kappa squared minus 2 kappa. Okay, so we'll just do that. Then the last term is quite straightforward. There's no need to factorize anything. It's already there by itself. Okay, so lastly, I'm just going to tidy the terms up before we can start solving this quadratic equation. So psi 1, okay, just make sure all these are dimensionless. So P, this is a dimension of P times V over RT. So that's a Z, or rather compressibility factor units of Z, or in other words, ratio. Okay, so let's see here. Let's see what how this psi 2 units are like. So the volumes here cancel out. The volumes here mostly cancel out. So yeah, V minus B over this whole volume term here over V square. So this is a V square term. So these ones will cancel to give you 1 over V at the bottom. Okay, RTC and RTC here will cancel. So you have a RT over PV. Okay, RT over PV. So psi 2 is also dimensionless. So far should be fine. Okay, so psi1 and psi2 are definitely dimensionless. Okay, and then what do? We want to multiply the psi2 throughout. Okay, how many times did I do that? Oh. Okay, let me multiply psi2 throughout. Psi2 goes here. Psi2 goes here. And psi2 goes here. Okay, so this was psi2 multiplied incorrectly. So psi2 goes here, psi2 goes here, psi2 goes here. Then I can remove the brackets. It's safe to remove the brackets now. So just want to be very careful about this. Okay, last but not least, let me bring TR over. Let me bring TR over. So I'll have a minus TR here. And the left-hand side, or right-hand side rather, will be 0. So let me factorize TR out. And you will have a final quadratic form that should look about right. Minus 1. So dw. So factorize TR out, you should be able to get this. So we have a quadratic formula for the square root of TR. Quadratic formula for the square root of TR. So psi1 and this psi2 thing will be let me write this out. Recall quadratic formula. Okay, so if I'm not wrong, this will be for ax squared plus bx plus c equals 0. I believe the formula is x equals negative b plus minus square root b square minus 4ac, then divide by 2a. So plus minus should be okay. What should plus minus be? Plus minus should be plus dot minus. Yes, that's how. Okay, literally plus minus, not PM like LaTeX. So that is over here. So for quadratic formula, what's the A? A is psi1 and psi2. All of this, A equals to this whole lot here. Okay. B is this psi2. And A, okay, it's minus psi2. Pardon me. Minus psi2. Okay. Okay, so it's minus psi2, all of this, and C is this term here. Okay, I think I might have got the order kind of mixed up, so I have to redo some things. So C is the constant, so that should be the first one. Okay, let's see. This should be the right term. So A is psi2 kappa square minus 1. B is psi2 or minus psi2 2 kappa square minus 2 kappa. C is psi1 plus psi2 1 plus kappa square plus 2 kappa. And then we solve for square root of TR. and then solve for TR. Okay, that after we get TR, we should be able to obtain our temperature quite easily using T equals to TR times TC. Okay, the temperature in Kelvin equals to TR times TC. Okay, so that's the basis for the solver. Okay, so now we have this. Okay, now we have this. I'm going to save this. Okay, I always like to add this first. Added quadratic formula for temperature. Okay, there's a lot of lines of text code. Now, what I want to do is to get to the actual coding. Okay, so I'm going to go to PREOS. So what it says here, yes, I want to have a temperature, get temperature solver. Okay, so let's start finding things. So what do we have? We need to calculate psi1. Okay, the nice thing about writing all this out, at least you know we know what we need to find. Okay, so psi1 is this. So it's PV minus B over RTC. Okay, let psi1. Okay, this should be a ratio. And what should this be? P times specific volume minus B. Okay, divide by, what's the molar gas constant? Okay, I need to copy and paste this over. Divide by what? R, molar gas constant, times what? TC, crit temperature. Yeah. Okay, P is pressure. Okay. I'll go watch -x test. So this just wants to make sure, I just want to make sure things can compile. Okay, so that's psi1. Psi1 is settled. Psi2 is now over here. There's this long bit of things to do. Let's see whether I can recycle code from the previous attempts. Okay, so this is A, 0.42747 over R squared TC squared over PC. So this is the A for the Ping Robinson. Okay, this is the A for the Ping Robinson. Or rather, was that Stoef Ridlish Kwong? Okay, let me see whether I can find alpha. Okay, so this is the numerator thing here. So I'm not going to call this the numerator. I'm just going to call this the, okay, this term. I'll just call this the alpha coefficient. Okay, alpha coefficient. There's this long string of numbers right here. Okay, so alpha coefficient is here. So I want V minus B over RTC. Okay, if you notice over here is like a psi1 sort of unit as well. But never mind. I'm going to do it. Okay, let me do this for psi2. Okay, so you see there's a lot of multiplication and division here. So one way to organize code, and I like to do this. One way to organize code is to use a let statement. Let psi2 equals, and now I'm going to nest everything in a bracket like this. Okay. nest everything in a bracket like this. Okay, and now I'll do a semicolon here. So sci2 will be whatever is left at the end of the function right here. So we do it like a function. So you see at the end of the function you usually do a return something, or you can also write pressure right here, and this will actually return the value. Okay, so what we are going to do is to just use this sort of naming convention. I'm not going to use the return because returning a value means returning to this function. So to return a value to sci2 here, then I will just, for example, put value right here. Okay, we will return sci2 will be this value. Okay. So let me just demonstrate that so it's easier. Okay, I'm going to make sure sci2 is definitely a ratio type. Okay. Okay, so yes, anyway, let me demonstrate this and hopefully things will clear up. Okay, so I will have this little left term equals to the specific volume minus B over molar gas constant times critical temperature. Okay, so this is this left term right here. Then I will have a denominator. Okay, so what's the denominator? Okay, so the denominator, let's see, where's the denominator? Did I calculate this before? Actually, I only did it in I would have done it in the pressure, get pressure of the Ping-Robinson gas. This is the numerator. There's the eccentricity term. Okay, let's see. Yes, this is the denominator thing. Molar volume times molar volume plus B. Molar volume times molar volume plus B plus B times molar volume minus B. So this is the denominator. Okay, so I'm going to do that. Okay. Okay, so molar volume and specific volume, they're the same thing. Let me do that here. Oh, specific vol. Okay, this should work. Okay, so this is the denominator, and I'm going to find sci2. Sci2 equals to left term times alpha coef divide by denominator. Okay, let's see whether I'm going to return sci2. So this is how you return sci2 inside this little thing. Okay, so sci2 is right here. Okay, sci2 equals to left term times alpha coef divided by denominator. So this is the sci2 I'm talking about here. So we have a sci2 and a sci1. So now we can just straight away compute A, B, and C. Okay, I'm just going to call this let ratio A equals to, so this is the one, sci2 times kappa, hold on here. I want to do a kappa square first. So this is a ratio as well. Kappa times kappa. Okay, sci2 times kappa square minus 1. Okay, and I need to do this as a ratio. New ratio 1.0. Okay, so that's the ratio A. I'm going to do ratio B now. Ratio B now. So what's ratio B? I'll have a minus psi 2 times 2.0 times kappa square minus 2.0 times kappa. 2.0 times kappa. Okay, so ratio B is minus psi 2 times 2.0 kappa square minus 2.0 times kappa. So let's do a ratio C. This is a ratio as well. And equals to psi 1 plus psi 2. 1 ratio new ratio 1.0 plus kappa square plus 2.0 times kappa. Okay, so that is the ratio C. Okay, all we need next is a quadratic solver. So I'm just going to make a new quadratic solver file. And this should be quite straightforward. Quadratic roots.rs. Okay, I'm going to have a pub mod here. Okay, mod quadratic roots. Okay, so quadratic roots, well, yeah, it's quite simple for quadratic roots. Okay, pub function find real roots, quadratic roots. So this is definitely going to take in three things. A, which is a ratio. I'm not going to do ratio. Okay. B ratio, C ratio, and what's it going to return? It will return a result, ratio, and I'm going to put some error type here. Okay, I'll just put a string as a placeholder. Okay, and I'm going to use OpenFOAM SI F64 star. You've seen this often enough. Okay, so let me go and import the error types as we did before. So error. Let's see whether I have a result. Oh, I don't have a result here. Find cubic roots. Okay, 3 real roots. And 1 real root. Okay, I don't have that here. Okay, maybe, yeah, I'm looking for the error that I coded in before. So let me look at the error. Cubic EOS error. Okay. Cubic EOS error. Okay, so I can put down here an error. No real temperature root. So that's something you likely will not encounter. But okay, so this is the cubic EOS error I wanted to import. Okay. Let me see, cubic EOS error. I'm going to put inside the quadratic roots here. It's not the best place to put the cubic EOS error because yeah, it's not the best place because I think quadratic roots it's you can use this function for many more things than just the cubic EOS solver, but for the time being, I'm just going to leave it as that. Okay, I'm not gonna do too much. I'm not gonna bother too much. So first, let's find the discriminant. Okay. Oh, there is a discriminant here. Okay, b squared minus 4ac. Okay, this will be a ratio equals to b times b minus 4.0 times a times c. Okay, so b squared minus 4ac. Okay, so if this thing is less than 0, okay, is less than ratio new ratio 1 point less than 0 or ratio 0, let me do 0, then I'll execute some line of code. Okay, let me import this. Okay, and I want to separate this out. That's how I like it. Okay, if v squared minus 4ac is less than 0, then I will have a cubic EOS error. Return cubic EOS error, and I'll have no real temperature root. Okay, so that's what I'm gonna have. I'm gonna put an error right here in the result. Okay. Otherwise, I will return the ratio. Okay, I will return minus b plus minus square root b squared minus 4ac. So let x1. Okay, and I need to return two ratios. Okay, so this right here is a fixed size array, a ratio of 2. Let me show you a fixed size array. Fixed size array Rust. Okay, so a fixed size array will look something like this. But you have the type will look like a square bracket. We will have the type here and then how many elements we should expect. So this is statically typed. Yeah, so the array is sort of statically typed, so if I'm not wrong. So basically yeah, the length of the array will be known at a compile time. Okay, so that is going to be the thing. So for sure, when you find quadratic roots, I'm going to have two distinct roots or at least two equal roots if the discriminant is more than 0 or equal to 0. So that's what we are going to be doing here. Okay, so x1 is a ratio. Okay, these are all dimensionless anyway, so it's minus b. I'm going to do this minus b plus b squared square minus 4ac square root. Okay, divide by 2.0 times a. Then I'm going to do the x2 as well, except this time it's a minus. And then I'm going to load both of these into the array. That solution array equals to x1 and x2. And then I'm going to return, okay, solution array. That's how I'm going to have my real quadratic roots. So this one's pretty simple. That don't need to think too much about it. Just takes a little bit of time to code. No, to be frank, you could find this in a library, but I'll just code it myself for the time being. Okay, so I'm going to go back to the real guesses right here and wrong file. Where's my preos? Okay, and I'm going to get my temperature solver. get temperature for the Ping Robinson gas. So so we have ratio A, B, and C. Okay, so let temperature array or square root reduced temp array, and this will be what? An array of ratio, and you have a size 2. This will be equals to what? Square root. Okay, let me see what I named it. P cubic roots, quadratic roots, find real quadratic roots. Okay, find real quadratic roots. Ratio A, ratio B, ratio C, and I'm going to put a question. I'm going to do, there are two ways you can do this. Okay, you can unwrap, and then I will import the quadratic roots. Okay, and I can use the unwrap. However, that's not really good for error propagation. So I'll show you how to deal with it later. So the reduced temperature array is as such. Okay, I'm going to let square root t. Well, this is not a square root t. Root. Okay, I'm just going to do the final thing. Let reduced temperature equals to square root reduced temp array, the first value and the second value. Let's see whether this works. Okay, then I'm going to return. Okay, oh, not yet. This is still a to-do. Let temperature equals to reduce. Let gas temperature equals to reduce temperature times the critical temperature. So that's what we scaled it by. So now we can return the gas temperature. And that's it. Let's see what's wrong with the thing here. Okay, it's expecting a temperature kind, but I am getting a kind. Okay, so basically when you get this kind of error for the, okay, it says expected trade temperature kind, found trade kind. When you see this kind of error, it's usually due to one of them being a temperature interval and the other one of them being a thermodynamic temperature. So for this is one of the things you can do is since critical temperature is already a thermodynamic temperature, okay, don't multiply it by a ratio, you just multiply it by a float. Okay, so I'm going to do a get ratio as such, and that should solve it. Okay, so why do you have this problem? Okay, because gas temperature is meant to be a thermodynamic temperature, not a temperature interval. Okay, so when you have a thermodynamic temperature and you multiply it by a ratio, you get a temperature interval. That's how the type system works. Okay. Okay, it's going to get a thermodynamic temperature here. Okay, things should compile. And I have the gas temperature. Now, having just a rule of thumb here, having unwraps like this is very bad practice usually if you want to have your code. So for this find temperature thing, we generally speaking, okay, we have a part of the code that is not guaranteed to always return a real root. Okay, so this find real quadratic roots function is not always guaranteed to give you a real root. So since that is the case, we should be returning a result rather than a thermodynamic temperature in order to handle the errors properly. Okay, so I have a cubic EOS error like so that I have a result. Okay, so at the bottom, I'm going to I'm going to wrap this gas temperature in the OK enum. And well, for the square root reduced temperature array, okay, there is a way you can do this. Okay, there's a way you can do this. First thing first, I'll show you the slow way, then I'll show you the really faster way. Okay, so this unwrap is the not so good way, so I'm gonna do away with this by commenting this out. However, of course, I will have the code there just for reference. Okay, let square root reduce temperature away. Okay, and this will be a ratio 2. It will be as such, it's the same thing. Okay, so first thing first, I'm going to get the reduced temp array result. So this is the slow way, yeah? This is the slow way. Equals to find real quadratic roots, ratio A, okay, ratio B, and ratio C. Okay. And what we learned before? What did we learn before? We learned to do a match statement. Okay, so equals to match reduce temperature array result. Now I'm going to do both of these. Okay. Fill match arms. Okay, so this took a little bit of time. Okay, so the OK variant, oops, the OK variant is going to have a array. So for this case, we just do the array. Okay, for the error variant, we have an error here. What we can do is just to return the error. Okay, return the error. Error. And that's it. Okay, so what is this part doing? Okay, so this find real quadratic roots is going to return a result. So there are two cases. One of them is that we have the array. Okay, if this thing runs okay, we can return the array and then we load this value into the square root reduced temperature array. If there's an error, then we return an error that causes this whole function to return this cubic EOS error enum. Okay, so that's the long way of doing it. Now let me then introduce the shorthand method, which is what you will often see in Rust code. You will just see this instead of all of this, right? Instead of all of this here, okay, you will just see this thing called the question mark. Okay, let square root reduce temperature array. Okay, and this will be a ratio 2, and this will equals to, all right, instead of doing unwrap, I just replace it by a question mark. Okay, this will do error propagation. Okay, what this error propagation does here, it's basically these two lines together. They squish it into one very concise line here. So this question mark operator is what we call error propagation. Okay, error propagation. Okay, so you can take a look at this a little bit more, but yeah, there should be the question mark thingy right here. Yeah. So this one is using question mark on a result value with the function type is allowed, blah blah. Okay, so just look for the part with the question mark. Okay, there's a lot of question mark here. Okay, let me go back. Question mark. Yes, I should use G and Control Shift G in here. Yes, a shortcut to propagating errors, the question mark operator. So this is the question mark operator, which actually propagates the error. So when we talk about propagating error, it's basically this bit of things here. So we get the result out first. If the result is sort of okay, if the result is okay, I mean, well, before we even do the result is okay, we match this result first. We use a match statement. If it's okay, then we continue on with the code. If there's an error, then we return this error right back here. We tell this function to return the error type. So that's what error propagation is. So this question mark here squishes that these two lines of code into one line, very neat and very concise. So that's what the question mark operator is for when you see these things in Rust code. Okay, so that's error propagation. Okay, so this is in the case that there are no real roots. We will tell this guy, okay, let's return an error, no real roots. Okay, so that's basically how the code works. So next again, we will have to test whether this code is is it working correctly. So if I want to make sure it works correctly, I'm going to recycle one of the tests here. Okay, I'm going to recycle one of the tests here. Let me put the temperature here. I'll call this the temperature test. Okay, temperature test. Okay, so I have all the same things right here. Critical temperature, steam temperature, pressure, and volume. Okay, and I'm going to get okay, I'm going to get the molar volume. Okay, so this is the molar volume. So I'm just going to get steam molar volume. So what I'm doing here is that I'm basically recycling the pressure test and, or rather the volume finding test, and I'm going to use it for temperature. Pardon, it's really long. I'm almost an hour long, but yeah, here, that's what we are doing here. So let's do that. There's a steam molar volume here. Okay, and the steam temperature is okay, what we expect. Okay, so I'm going to delete this assert part, and I'm going to just find the temperature. Okay, find temperature using the Payne-Robinson equation of state. So get temperature Payne-Robinson gas. That is what I'm going to do. Let test gas result temperature. I'm going to do a thermodynamic temperature. This will be the type. Goes to find temperature. Get temperature Payne-Robinson gas. So there are a few things here. And then I will just do an unwrap. Okay, so let's take a look. The specific volume will be the steam molar volume. Pressure here is the steam pressure. Eccentricity factor. Where's the eccentricity factor? Oh, I'll do it here. Okay. Temperature. Okay, so this is the result temperature. Okay, I should be putting volume. KST molar volume. Yes, so that's the correct thing. Expected steam temperature, I can just take this out. So I'm going to assert approximately equal the two temperatures. And I'm going to do that in Kelvin because we are returning these two temperatures in Kelvin. So gas result temperature and let's see, expected steam temperature. Okay, so I rather make the, I'll call this steam result temperature. And my keyboard's funny. Okay, and let me put Kelvin right here. Let's see whether this works. Okay, so for one thing, I do have numbers here, but it's sort of negative. So let's see what was wrong. Okay. So okay, let hold on for a while. Yeah, so I guess my error was in multiplying these two roots together. Well, assuming that would work, but maybe that's not the way to do it. So I need to actually do a reduced temperature 1 and 2. So this is the two reduced temperatures, right? I mean, here are the two square roots of the reduced temperature here, right? Okay, 0 and 1. And somehow I need to sort of make sure to find, yeah, because there are two roots. So we could actually have two possible values of reduced temperature or the square root of reduced temperature. So I'm not supposed to do this. I'm supposed to do this. Okay, either have both of them 0 or both of them 1. So this is something I need to do later on. But let me try both of them 0 first. Okay, if both of them 0, this actually works. If both of them 1, this also works. Okay, so let me reduce the error tolerance to within 0.001. Okay, this may fail. So this is 889. That's one of the temperature roots. And let me try both of them 0 just to test. Okay, so 886. So I mean, this whether it's whether you have either temperature root, it sort of gives you, it gets you pretty close to this it gets you pretty close to this answer anyhow. I'm not entirely sure why, but yeah, just how this equation seems to be working. Okay. Yeah, think, well, I'll put this as a to do which root is the correct one or the better one to use, because both of them in this particular case it's fine, but what if they are, like, you know, quite far apart? Then what do we do about it? So that's something we need to consider. I'll probably leave that to next time. Okay, bye.